In this video, I'll be covering the previous year GATE questions from the topics irreversibility, availability, and pure substances. So let's see the first question. The maximum theoretical work obtainable when a system interacts to equilibrium with a reference environment is called. Okay, this definition is of which term? This is the definition of the term exergy, that when a system undergoes through a process, the maximum theoretical work obtainable is exergy. Okay, you know entropy, you know enthalpy. This is degree of randomness. Entropy, rothalpy is actually a term which is used in turbo machines. Okay, let's move on to the next question. A source at a temperature of 500 Kelvin provides 1000 kilojoule of heat. The temperature of environment is 27 degrees Celsius, that is 300 Kelvin. Okay, maximum useful work that can be obtained from the heat source. Very simple question, basic question, that we know that maximum useful work is obtained when a Carnot engine works between the heat source and the ambient. Okay, so you must have studied this equation, that is 1 minus T naught by T1 upon into Q1. Okay, put the values. You have to find the maximum useful work in kilojoules. Okay, so Q1 is 1000 kilojoule. I will put the value in kilojoule only because we need the answer in kilojoule. 1 minus 300 by 500. Okay, that implies maximum useful work will be 400 kilojoule. Okay, okay, a very simple question. Next is, one side of a wall is maintained at 400 Kelvin and the other is maintained at 300 Kelvin. Rate of heat transfer through the wall is 1000 watt. Surrounding temperature is 25 degrees Celsius, that is, let me write it as 298 Kelvin. Assuming no generation of heat within the wall, the irreversibility, okay, in what? What is irreversibility? It is loss of available energy. Or how do you write irreversibility? W max minus W actual. Okay, there is one more way, that is Gauss-Stodola theorem. You must have heard of this theorem, Gauss-Stodola theorem. That is, irreversibility is equal to T naught delta S, where T naught is the ambient temperature, which is 298 Kelvin. So if we find delta S, we find irreversibility. Okay, and this type of question we have done, like in the previous question, in the previous video, that this wall is at 400 Kelvin, this is at 300 Kelvin, and 1000 watt of heat energy is going from this wall to this wall. So delta S will be Q1 by T1 plus Q2 by T2. However, from this wall the heat is going away, so this will be with a negative sign, and the heat is absorbed in this wall, so this will be with a positive sign. Okay, temperatures are not changing, so delta S is equal to minus 1000 upon T1 is 400 plus 1000 upon 300. Solve this. Delta S will be 0.83 watt per Kelvin. Okay, put this delta S here. Change in entropy, irreversibility will be 298 into 0.83 watt per Kelvin, which will be 248.33 watt. Okay, we have got the answer in watt, we have to fill the answer in watt. Okay, next question. A mass m of a perfect gas, pressure P1 and volume V1 undergoes an isothermal process. Okay, the final pressure is P2 and the volume is V2. The work done on the system is considered as positive. Oh, okay. So this is the important line, that the work done on the system is considered as positive. So that means the work done by the system will be negative. Okay, R is gas constant, T is the temperature, then the work done in the process is okay. So if the work done on the system is considered as positive, work done by the system will be considered as negative. Okay, when we solve this, what do we get in case of isothermal process? We get minus P1 V1 ln P1 by P2. So I guess option B is the answer. So this was the key line, nothing else. Okay, let's move on to the next question. Pretty simple questions these are, just formula based questions, and all you have to do is identify the keywords, the key lines. So the next question from pure substance is, a rigid container of volume 0.5 meter cube contains 1 kg of water at 120 degrees Celsius. Okay, specific volume of the liquid is given, specific volume of the gas is also given. This is small v. Okay, the state of water is a very simple question. You have been given specific volume of the liquid fluid and and you have been given the specific volume of the gas. What can you do? You just find the specific volume of this water at 120 degrees Celsius. It will be 0.5 upon 1, that is 0.5 meter cube per kg. Now compare it with these values. What do you find? That V is less than Vg, however it is greater than Vf. So can I say that it is a mixture of saturated liquid and saturated vapor? Okay, C is the answer. Next question. For water at 25 degrees Celsius, I will change it in Kelvin, 298 Kelvin, dP by dTs. Okay, whenever you look at this term, your mind should go towards Clausius-Clapeyron equation. Okay, that there can be a possibility of the usage of that equation in this question, a possibility. Okay, dP by dTs is equal to 0.189 kilopascal per Kelvin. Kilopascal. PS is the saturation pressure in kilopascal and Ts is the saturation temperature in Kelvin. The specific volume of the dry saturated vapor is given. Assuming that specific volume of liquid is negligible in comparison with that of vapor. Okay, it has already been given that using the Clausius-Clapeyron equation. Wow. And Clausius-Clapeyron equation, estimate the enthalpy of evaporation of water at 25 degrees Celsius. Very easy question, very easy question, directly on the basis of Clausius-Clapeyron equation. What is Clausius-Clapeyron equation? It is dPs by dTs. It states that it is equal to HFG upon saturation temperature into VFG. Okay, HFG we have to find out. dP by dTs is equal to 0.189 kilopascal per Kelvin. Okay, so that means if I don't change kilopascal per Kelvin in Pascal per Kelvin, I will get HFG in kilojoule per kg. Okay, and I need the answer in kilojoule per kg, so let it go this way, 0.189 kilopascal per Kelvin. Okay, now TS is 298 Kelvin. 298 Kelvin. Great. VFG. VFG is VG minus VF. VG is 43.38 and I will ignore VF because it has been given that VG is much greater than VF. Solve this. get the answer of HFG, which is equal to 2443.248 kilojoule per kg. Okay, next question. The incorrect statement about the characteristics of critical point of a pure substance. Critical point. Okay. There is no constant temperature vaporization process. Yes, it is correct. See, let me draw this TS, a rough dome. So at this point, there is no constant temperature vaporization process. Yes, it is correct because the liquid directly flashes into vapor. Okay, so this is correct. Second, it has point of inflection with zero slope. Yes, this is a point of inflection with zero slope. It is also correct. Third, the ice directly converts from solid phase to vapor phase. No, this is wrong because it is the liquid which converts directly to vapor phase. It directly flashes into vapor phase. Okay, no need to check fourth option, but yes, we will check it, and you should check it too. I mean, it gives more assurance, whatever you can say. So the D option is saturated liquid and saturated vapor states are identical. Yes, it is correct. Okay, so our answer is C. Next question is 1 kg of an ideal gas, mass is 1 kg of an ideal gas constant is, the value is given, specific heat at constant volume, the value is also given in joule per kilogram Kelvin. Note down the units at 1 bar and 300 Kelvin. Initial conditions are given, is contained in a sealed rigid container. Okay, keyword, during an adiabatic process, keyword, 100 kilojoule of work is done on the system by a stirrer. Okay, catch the keywords. The increase in entropy of the system, you have to find the increase in entropy of the system. Okay, so a rough box, rough sealed rigid cylinder. Okay, okay, this will be a cylinder. So suppose this is the stirrer. Okay, adiabatic process. Okay, can I say that the work done on the system by the stirrer will increase the internal energy of the gas, or I will say will only increase the internal energy of the gas, because this is an adiabatic process, no heat is going out, so del Q is 0. Okay, let me prove it. From first law, del Q is equal to du dw. Okay, this is 0, so dw will be equal to, okay, minus of du. So what I have said, that the work done by the stirrer will increase its internal energy, because this work done, this stirrer sorry, this stirrer will eventually provide heat to the gas, which will raise its temperature. Okay, and that we have proven here. Okay, now 100 kilojoule of work is done on the system, so that implies work done is minus 100 kilojoule. Okay, so put the value here. 100 is equal to m cv delta t, that is t2 minus t1. Okay, what is m is 1 kg, cv, this is in kilojoule, so cv will be in kilojoule, that is 1 kilojoule. This is 1, this is 1. T2 minus T1, what is T1? T1 is 300 Kelvin, so we get T2 is equal to 400 Kelvin. Okay, Now you have to find entropy. Very simple, directly formula based. Delta S is equal to, you have to find entropy of the system, not specific entropy, joule per Kelvin. Okay, so that will be m CV ln T2 by T1, you read this formula, plus m R ln V2 by V1. Okay, V2 is equal to V1 because it is a sealed rigid cylinder. This becomes 0. M is 1, CV is 1000 because you have to give the answer in joule per Kelvin. ln 400 upon 300. That implies delta S is equal to 287.68 joule per Kelvin. So this will be the answer. Okay, next question. One kilogram of an ideal gas, 1 kg of an ideal gas constant is given, undergoes an irreversible process from state 1 conditions are given to state 2 conditions are again given. 300 Kelvin, 300 Kelvin. What is happening today? So the temperature is constant. The change in specific entropy of the gas, specific entropy, okay, of the gas in joule per kilogram Kelvin. Delta S, directly formula based again. Delta S is equal to Cp ln T2 by T1 minus R ln P2 by P1. Okay, this is the formula. We have read this formula. T2 by T1, Tt is same. This value becomes 0. R is 287. The value has been given in joule per kilogram Kelvin. You have to find the answer in joule per kilogram Kelvin. Okay, solve this. Get the answer as minus 198.93 joule per kilogram Kelvin. Okay, basic question, very easy question. Yeah, let's move on to the next question. Which one of the following statements is correct for a superheated vapor? Okay, its pressure is less than the saturation. Which one of the following statements is correct for a superheated vapor? Its pressure is less than the saturation pressure at a given temperature. Let's prove it by drawing a rough TS diagram. Okay, this is a rough dome. Okay, at a given temperature, suppose T1 is the given temperature, I will draw a dotted line. Okay, so consider this state, superheated state. This is the corresponding saturation pressure for this temperature. Okay, so its pressure is less than the saturation pressure at a given temperature. Yes, it is less because this constant pressure line is like this. This is P1 and the constant pressure line passing through this state will be P2 and P2 is less than P1. Okay, so we get A as our answer. However, I will prove other options also. Its temperature is less than the saturation temperature at a given pressure. Okay, at a given pressure, this at a given pressure P1, its temperature is less than the saturation temperature. This is saturation temperature, and let us consider this. Let us consider this point. You can see that this temperature is more than the saturation temperature for a given pressure. Okay, its volume is less than the volume of the saturated vapor. No, it is wrong. Its volume will be more than the volume of the saturated vapor at a given temperature. Its enthalpy is less than the enthalpy of the saturated vapor at a given pressure. Again, it is wrong. Its enthalpy will be more than the enthalpy of the saturated vapor at a given pressure. So these 2 points, were important. I mean, these 2 points were a bit confusing. However, always try to solve these questions by constructing a TS diagram. Okay, thank you.